The universe is approximately 13.8 billion years old, and it has been expanding ever since the Big Bang. Galaxies are moving away from one another, space itself is stretching, and the overall structure of the cosmos is constantly evolving. One of the most important questions in modern cosmology is not just how the universe began, but how it will eventually end. Scientists have developed several well-supported theoretical models that describe possible long-term futures of the universe. These models are based on observations of cosmic expansion, measurements of dark energy, and known physical laws, such as thermodynamics and general relativity. In this educational documentary, we will explore four major scientific scenarios: the Big Freeze, the Big Rip, the Big Crunch, vacuum decay. We will also examine what these scenarios mean for Earth and for the long-term future of human life. Why the universe has an ending. The universe operates under physical laws that govern energy, matter, and time. One of the most important principles is the second law of thermodynamics, which states that entropy, or disorder, tends to increase over time. This means that energy becomes more evenly distributed and less useful for doing work. In addition, stars consume nuclear fuel, galaxies merge and eventually run out of star-forming material, black holes slowly lose mass through Hawking radiation, space continues expanding due to dark energy. These processes imply that the universe is not static and not eternal in its current form. While the total lifespan of the cosmos may extend far beyond anything humans can experience, physics strongly suggests that all structure and activity will eventually decline. The exact outcome depends on one unknown factor: the long-term behavior of dark energy. The Big Freeze, also known as heat death, is the most widely accepted scenario among cosmologists. How it works. In this model, the universe continues expanding forever at an accelerating rate. As space expands, galaxies drift farther apart. Star-forming gas becomes too diffuse. Fewer new stars are created, existing stars gradually burn out. Timeline: in approximately 5 billion years, the sun becomes a red giant, making Earth uninhabitable. In approximately 100 trillion years, the last stars stop shining. In approximately 10 to the power of 100 years, black holes evaporate completely. After that, the universe becomes extremely cold, dark, and empty. Final state: no stars, no planets with energy sources, only low-energy particles spread across vast distances. The universe does not collapse or explode. It simply reaches a state of maximum entropy, where no meaningful physical processes can continue. The Big Rip is a more extreme scenario that depends on dark energy becoming stronger over time. How it works. If dark energy increases instead of remaining constant, the expansion of the universe would accelerate more and more rapidly. Eventually, this force would overcome all other fundamental forces. Stages of the Big Rip. Galaxies break apart. Star systems become unbound. Planets drift away from their stars. Molecules split. Atoms are torn apart. Subatomic particles disintegrate. Final outcome. In the final moments, even space-time itself is disrupted. There is no stable structure left in the universe. While current data does not strongly support this outcome, it remains a theoretical possibility based on certain dark energy models. The Big Crunch represents the opposite extreme. How it works. If the total mass energy of the universe is high enough, gravity could eventually overcome cosmic expansion. The universe would stop expanding and begin contracting. Effects. Galaxies move closer together. Cosmic temperatures increase. Star formation accelerates. Matter becomes more densely packed. Eventually, all matter collapses into a single, extremely dense point, similar to the conditions at the beginning of the Big Bang. Theoretical implications. Some models propose that a Big Crunch could trigger a new expansion event, resulting in a cyclic universe. However, current observations suggest that the universe is not slowing down in its expansion, making the Big Crunch less likely than the Big Freeze. Vacuum decay is a more speculative but scientifically grounded concept. What is it? In quantum physics, the universe may exist in a false vacuum, a stable-looking state that is not truly the lowest possible energy configuration. If a lower energy state exists, a random quantum event could trigger a transition. What happens to Earth? Regardless of which cosmic ending occurs, Earth's fate is determined much sooner. The Sun's life cycle. In approximately 5 billion years, the Sun becomes a red giant. Earth's oceans evaporate. Surface temperatures exceed 1,000 degrees Celsius. The planet may be engulfed or stripped bare. Long-term Earth outcomes. Big freeze. Earth becomes a frozen, airless rock. Big rip. Earth is physically torn apart. Big crunch. Earth is destroyed during cosmic collapse vacuum decay. Earth disappears instantly. Earth cannot survive indefinitely under any cosmological model. What happens to humans? The long-term survival of humanity depends on technological and biological evolution. Possible future adaptations, space colonization, artificial habitats, advanced energy harvesting, genetic or cybernetic enhancement. However, even the most advanced civilization cannot override the fundamental laws of physics. Eventually, energy sources will run out, information processing will cease, conscious life will no longer be possible. This conclusion is based on thermodynamic limits and cosmic expansion. Studying the end of the universe is not about fear. It is about understanding. The laws of physics. The long-term behavior of space-time, humanity's place in cosmic history. It helps scientists refine cosmological models and deepen our understanding of dark energy, gravity, and quantum mechanics. It also provides perspective. Life is rare. Time is limited. Scientific knowledge is powerful. The universe will not last forever in its current form. Whether it ends in a slow fade, a violent tear, a collapse, or a sudden quantum transition, all scientific evidence suggests that change is inevitable. But for now, the universe is active, structured, and capable of supporting life. Understanding its future allows us to better appreciate its present. If you found this documentary informative, subscribe for more science-based space content, like the video to support educational creators, and comment below, which scenario do you think is most scientifically likely? Because the future of the universe is still being written, and science is how we learn to read it.